Today is the third video from 3.1.1 and it's about the time of flight mass spectrometer. Remember, for all your revision needs, head over to www.educationc.xyz. Alright, so today's topic is completely new. There was none of this on the GCSE course whatsoever, and on top of that, there has not been a single year since 2017 that this has not come up, including 2022 when I sat my A-Levels. So with that, it's probably important to get your head around it best as you can. So what's it all about? The mass spectrometer is this portion of the photo. It's a box and it's about 1.5 meters long. If we look at the name of the machine, the mass spectrometer, the word mass means what it always has done. A car is about 1,000 kilograms. A human is about 80 kilograms. But the mass we're looking at in this case, relative atomic mass or molecular. A time of flight mass spectrometer is used to calculate the relative atomic mass of a sample of an element or the relative molecular mass for a sample of a molecule. It does this by differentiating between heavier and lighter isotopes of the element or molecules made up of these isotopes. The heavier it is, as you'll find out later in this video, the longer it takes to drift down the tube, the longer the time of flight. I've just told you this because essentially, if you're wondering why on earth this random machine fits into this topic, it's because of the definition of relative atomic mass. The average mass of an atom from a sample of an element on a scale where 1/12 of carbon-12 is 1. In that phrase that you've heard in the past two videos, the word average comes up right at the start. So how did they put a single number down on the periodic table? For example, 12.0 is carbon. It's what's written down on your AQA table that you get given in the exam, by using a mass spectrometer. Before we start doing any of the analytical side of this, there are 4 basic principles of a time of flight mass spectrometer that you're expected to know. This is a simplified version of the inside of a time of flight mass spectrometer. 1, 2, 3, which is all the way there, and 4. Now, AQA, for some reason, in their infinite wisdom, have decided you need to know about all 4 and what goes on inside a mass spectrometer. The first stage is ionization. There are 2 types of ionization, or 2 methods that you need to know about, and you can be asked about both, and they are both distinct. First is electron collision or electron gun. 2 names for the same thing. In this method of ionization, a electron gun or filament of wire gives off high energy electrons. These collide with the individual particles, the molecules or the atoms in your sample, and in turn form 1+ ions. Imagine it like you got a nucleus here and then electrons around the outside. This isn't scientifically accurate to say the least, however it's a good way to remember. And we've got a ray gun out of like Star Trek or something, and then this is firing electrons, and eventually one of them will hit one and shoot it off. You're left with the same thing, 1, 2, 3, 4, 5, 6. Instead of the original 7 on this. So now you've got a 1+ and another electron floating around. We can write an equation for that, of course. X, which is in the gas phase, becomes X plus E minus. An electron is knocked off, you get a positive charge, and the electron's there as well. The second way to ionize a sample is known as electrospray. In electrospray, the sample is dissolved into a solvent. The solvent is inert and volatile. Inert means no reaction, and volatile means it can be removed easily, because sometimes you have a very limited quantity of a sample and you don't want to waste it by dissolving it in a sample and then never being able to get it back. Dissolving it in a solvent, sorry. After it being dissolved in a solvent, this mixture is then forced through a hypodermic needle, or just a very fine needle. This needle is connected to a high voltage power supply. We're talking 400,000 volts or more, and this causes a H+ ion or proton to be donated from the solvent to the sample. This is the most key thing to remember, because the AR/MR will increase by 1. In electron gun, there is no addition of a proton. In electrospray, there is a addition of a proton, and therefore an addition in the mass unit to each ion. The second stage of the 4 is acceleration, and in this, all of the ions that we've just formed in the ionization stage are given the same amount of kinetic energy. And this is thanks to an applied electric field. And this leads very nicely onto the ion drift stage. If you remember back to GCSE physics, kinetic energy equals a half mv squared, where m is mass and v is velocity. If kinetic energy equals a half mv squared and all the ions get given the same amount of kinetic energy, then surely the heavier ions with the bigger value for m will have a smaller value for v to compensate for the difference. This leads straight into the ion drift stage. Due to heavier ions having a greater mass, therefore a slower velocity, they take longer to drift down the tube in the time of flight mass spectrometer. This is how, as I said at the start of the video, you'll realize when we get to it, the machine differentiates between the heavier isotopes and heavier isotope containing compounds. Should also mention, not just the drift stage, but the entire mass spectrometer tube is a vacuum. That way, air resistance is not a factor. The fourth and final stage or principle of a time of flight mass spectrometer, according to AQA, is detection. This is where the 1+ ions become neutral again. They hit a negative plate, they gain an electron, and in doing so, induce a current in the circuit attached to the detector plate. The size of this current is directly proportional to the abundance of the isotope hitting the plate at that time. Like we said in the last stage, the heavier ones hit later than the lighter ones. That's exactly how the machine can tell the difference between the lighter and the heavier ions, and also know how abundant one relative atomic mass isotope is compared to another with a different relative atomic mass. In terms of the 4 principles, that is everything you need to know comprehensively covered. What we're going to go on to now is uses for the data that's produced and the type of questions that they ask in the exams. There's 2 types I want to cover. It's calculating relative atomic mass from a sample, and also a 5-mark style question that comes up almost every single year. This is the type of graph you get out of a mass spectrometer. It's called a mass spectrum. It tells you information about the relative abundance, as we've just discussed, and also the MZ ratio. Now, MZ stands for mass divided by charge. And you might be thinking, hold on a minute, what? Why is it not just mass? But if you think back just literally 5 seconds ago when we talked about the ionization thing, everything that hits the detector is an ion. At A-level especially, the charge of the ions is almost without fail always, I've never seen it not be 1. So it's just mass divided by 1. So you can think of this really as just mass. This is chlorine's mass spectrum, by the way. I didn't mention that. And chlorine on the periodic table is 35.5. And you might be looking at this thinking, how on earth did they get there? Well, to calculate any relative atomic mass from a mass spectrum like this, the first thing we do is multiply 3 by 35 and 1 by 37. And that gives you a grand total of 142. Then we divide that by the total relative abundance. So 3 add 1, which is 4, the grand total, as expected, of 35.5. Just had to check myself there. Let's look at this in a more exam style setting. A sample of titanium was ionized by electron impact, that's key information, in a time of flight mass spectrometer. Information was written in the table below. Calculate, that's what it's asking us to do. So give it a box, the relative atomic mass in this sample. Give your answer to 1 decimal place. Let's scribble down what we know. Electron impact, therefore no. H+ ion, therefore don't, -1 essentially from each of these MZ values, which you would have to do if a H+ ion was added on. You may also have realized though that this time abundance is given as a percentage rather than a relative scale. All that means though, instead of adding up the total abundance as we did on the previous example of chlorine and getting 4, we're going to get 100. So the thing we're going to divide by overall is still the total abundance, but it's just 100 because it's percentage. The best way to think about what this means in terms of the abundance percentage being 9.1 is that out of every 100 ions that came into contact with the detector plate, 9.1 of that 100 had an MZ value of 46. So 7.8 out of every 100 had an MZ of 47, and 74.6% had an MZ of 48. 8.5 out of the 100 had an MZ of 49. Let's do the calculation now as we did before. That gives us the total of 4,782.5. Remember, divide by 100 to get 47.825. Read the question last time before we write our final answer. 1 decimal place, therefore 47.8. And that is the correct answer. And now the final style of calculation, as you can see, with 5 marks. Let's read the question and apply the approach that we always apply. Box the command words, underline key information, scribble down what we know, and then go. Let's read. A barium ion, that's key information, travels down the time of flight tube with a kinetic energy, so kinetic energy of 3.65 times 10 to the minus 16 joules. The ion takes 2.71 times 10 to the minus 5 seconds to reach the detector. We've been given the kinetic energy equation. Mass has to be in kilograms. Speed has to be in meters per second. We've also been given the Avogadro constant, which if you've not reached this yet in your A-level, but I'm sure you will remember it from GCSE, this number is how many atoms in a mole. Every mole has 6.022 times 10 to the 23 atoms in it. The mass of a mole changes depending on what we're talking about. So 1 mole of barium, for example, has a mass of 137 grams. Now, command word, calculate in meters the length of the flight tube and give your answer to an appropriate number of significant figures. Let's scribble down everything we know. Kinetic energy is a half mv squared. Considering we're talking about 1 ion, we're probably going to need to know the mass of it, so then we can know the velocity of it, and we already know the kinetic energy. And how do we link that to? Well, velocity equals distance over time, or speed equals distance over time. And this is the missing link, if you will, that isn't written down. So where can we start? What do we know? We've been given time. We've been given kinetic energy. Can we work out mass of 1 ion? Yes, we can. So let's do that first. The mass of 1 mole, as we know, is just 137 grams. And that is 6.022 times 10 to the 23 ions. So if we divide that by 6.022 times 10 to the 23, that's the mass of 1 ion in grams, and that gives us a nice small tiny number of 2.27499 times 10 to the minus 22 grams, and that's 1 ion. Remember, in the question, mass has to be in kilograms, so we need to divide this mass by 1,000, and that is kilograms from grams because we're in grams, and that is 2.27499 times 10 to the minus 25 kilograms. We're getting somewhere even closer now, because the one thing we need to work out the distance is the velocity, and we have mass, we have kinetic energy, so we can work out velocity. Let's put the numbers we know into the kinetic energy equation. 3.65 times 10 to the minus 16 is a half. 2.27499 times 10 to the minus 25 times v squared. We can rearrange this equation by multiplying both sides by 2 to get rid of the half, and then dividing both sides by this, which is the mass. Then we will have a number equivalent velocity squared. Velocity squared is 328,802,920. Square root of both sides to get 56,646 meters per second. And now simply that equals distance over time. Multiply both sides by time, which we were given in the question, times 2.71 times 10 to the minus 5. 1.53514 meters. It asks for an appropriate number of significant figures, and that simply means, always means, the piece of data with the least significant figures. So the least significant is 3. So we must do 3 significant figures, 1.54 meters. And that is the final answer to that question. Remember, the website's got everything you need to revise from. You've got these videos indexed more neatly on the website. Everything we talk about in note form, every exam question that's ever been asked with a video walkthrough like this. And on top of that, help to get into university. So thank you for watching, and I'll see you next time, boys. Come on.